Okay, so up until now, we've been finding the formulas for ionic compounds through this process, right? So we find our metal, and we draw out some atoms with their electrons, right? 2 valence electrons in a magnesium atom. And then we find our nonmetal and we draw out its valence electrons. So there's 5 in this phosphorus. And then we were taking an electron from here, putting it over there, and then we take one from here and we put it over here, right? And I still need more, so we're gonna move another one here. But now this still has one, so we're gonna have to move it to here, and then this to fill that spot, and then this to fill that spot. And I can see that I need 1, 2, 3 magnesium atoms, so I end up with the formula of Mg3, and then I used 1, 2 phosphorus atoms, right? And we never touched that one. Okay. Well, if you look at the oxidation numbers, the ion formulas for these, each of our magnesium atoms lost 2 electrons, which gives it a 2+ charge. And each of our phosphorus atoms here gained 3 electrons, which gives it a P3- charge. Well, if you take a look at this, I end up with a 3 right there, don't I? And I end up with a 2 right there. The reason that's going to happen is because if I've got 2 extra electrons here and 3 holes here, I'm going to end up needing to move 6 electrons so that I've taken the same number from here and put them into the holes here. It's like adding fractions with unlike denominators. You can just multiply the 2 numbers together. Okay, and then I would divide that by the number. So there's a complicated reason for why, but what I need you to understand right now is that we don't have to do this process anymore. This is long and complicated. Scientists don't actually do this process. Instead, all they do is pick up the numbers from their oxidation and drop them down here. So let's look at some examples like that so you can see where it goes. Okay, now in the last section, you should at this point have ion names. So if I wrote out something like, let's say, calcium, oops, there's a U in there, calcium chloride, you know that I'm going to look up the calcium and I'm going to find its oxidation number, which is a 2+. And when you see the IDE ending here, usually you're going to look up a chlorine atom. So we're going to take that Cl, and it has a -1 oxidation number, and we don't write ones when we do ion symbols. Okay. And so we're going to take the numbers, just the numbers, and pick this 2 up, move it over here to the chlorine, and we're going to pick up this invisible 1 that's right there, and we're going to move it over here to the calcium, so that when I'm done, I have a Ca with an invisible 1 after it, Cl2. Okay. Something similar would happen if, say, I had aluminum phosphide. Okay. I would have an Al3+ and a P3-. But if we went through this process right here and I had 1, 2, 3 to pass and 1, 2, 3 holes, I would only need 1. I'd take these 3 and pass them over here. I would need 1 of each. Remember that when we do ionic compounds, the formula we find, this object is called a formula unit, and it is a lowest ratio of terms. So really, I only need 1 aluminum and 1 phosphorus atom. Okay, so what we would do is before we crossed them, we're going to come back and reduce them down to 1s. And then we can take those 1s and move them. Okay, but we don't write 1s, so we end up just with an ALP, like so. Let's do 2 more examples. Okay, if I had, say, copper 2 nitride, I would have Cu2+ and an N3-. And I could take the 3 and put it after the copper. And I could take the 2 and put it after the nitrogen. And we would get a Cu3N2. Okay. One more. If I had tin IV, that's 4, remember, sulfide. Okay. My tin 4 is SN4 plus, because that tells me the oxidation number, simply a 4, always positive. Sulfide, we use the sulfur, is an S2 minus. Okay. Again, we look at our numbers, and because 4 to 2, it is not a lowest ratio, we reduce them to 2 and 1, and then we'll pick them up, move this over here, and the 2 over there, and we'll be left with an SN invisible 1, S2, just like that. Okay, good luck.